Hi, welcome back to Sover, the Nonograms. I had to rename it to avoid possible copyright issues, but that's only the second most remarkable size change because the solver can now handle boards that are really huge, such as this board which was made by my homie Piero, or this board from the thumbnail which is from my other homie Willem, or this board which is literally because it's the word forward. This video is about explaining how the new solver works, so it's gonna be pretty complex and it's been really difficult to make. So I hope you'll enjoy it and I hope you won't mind that you probably won't understand everything and that you can just appreciate how extremely complicated it is. But before we could get into how the solver works, let's go over what nonograms even are and how the old solver worked. The goal is to color in certain tiles in a grid and to leave out some other tiles. You can also put X's to indicate that the tile couldn't be colored in, but those are only there to make your life easier. The way you figure out which tiles to color in is by using the numbers next to each row and column. I'm going to call those numbers clues from now on. Clues indicate how many consecutive tiles are colored in. So this 3 means that the line has 3 colored tiles that are all connected. So there are 3 different possibilities for this line. And you couldn't make any of them without the middle tile, so you can just color that one in from the start. But some lines have multiple clues which are the same as before, but the separate clues cannot be connected. So this 1-2 line also has 3 possibilities. And you need the 4th tile for all of them, so you can just color that one in from the start as well. And what we've just done is exactly how the old solver used to work as well. It generated every possible solution and then it colored in the tiles that every solution had. Except in a real puzzle you might have some axes in a line, and also you can have tiles that are already colored in. So the solver had to ignore every possibility that couldn't exist on the line, but it was extremely simple. So why did I make a new one? Well, as you can see on this graph, the solver slows down a lot when the lines get too big. And by too big I mean above 20 tiles. And that's due to the fact that there are a lot of possibilities at those sizes. But I really wanted to have bigger boards in my game, and I thought I could make a better solver in just a few days. I was wrong, it took 2 weeks, and it became the most complicated thing I've ever made. But the good news is that I can tell you what it does pretty easily. It just explaining why it does those would be extremely difficult. So let me tell you what the new solver does without any explanation. I'll show you the name of every function I'll be talking about in the corner for anyone brave enough to look at the source code. It starts out by creating the left and rightmost possibilities like this, and then it saves the minimum and maximum positions for each clue based on the left and rightmost lines. These are actually called tile spans in the code, but there are going to be other spans later on, so I just refer to these as min and max. Also keep in mind that the counting starts at 0, so the first tile is actually the 0th tile. Now with the left and rightmost possibilities share tiles that belong to the same clue, then it can just color them in from the start. And for each colored tile that is connected, save their start and end positions, how many empty spaces there are to the left and right, and whether it has the chance to connect to another colored tile to the left and right. These are referred to as field tiles in the code, field being the same as colored in. So from now on when I say field tiles, I'm referring to these values. Now this is a bit complex, but for each field tile, get which clues could belong to them based on the min and max positions. The clues also start at 0, but since they're numbers to begin with, I just use the alphabet to refer to their positions for this video. Now group together the field tiles that could be connected, so the ones that aren't separated by an X, and get the min and max clues that they can have, and then truncate those using their neighboring groups. So like a group's max clue has to be smaller than the max clue of the next group, and the min clue has to be bigger than the min clue of the previous group. If two field tiles share their only clue, then make them into one big field tile. If a field tile has only one clue, then it has to belong to that clue, and if another field tile thinks that it could have that clue as well, but the connection needed would be too big, then that's not possible, so it needs to remove that one. And then truncate the min and max positions of the clues. If a field tile only has one clue, then the min and max could only be around that field tile with the radius of the remaining clue. And if the min and max would touch another field tile that doesn't have that clue, then also truncate it. And if any of the clues belonging to the field tiles have changed at all, then repeat all of the previous steps. And then with each repeat, truncate the min and max positions even more if they start or end in an X, or if the tile before their start or the tile after the end is colored in, or if there's not enough space without X's from the start and end to fit the clue. This one is recalled each time the min and max positions are changed. And for each field tile, save how many spaces there are to the left and right that it could grow in without any issues, using the min and max positions and heavily using the belonging clues of that field tile, and remove them if they wouldn't fit the spaces. And X out a tile if the maximum space to the left or right is 0, and then fill in tiles using spaces and the minimum size that a field tile has. Now make a list of every span of tiles that don't have X's in them, and save it based on whether it has field tiles in it or not. And for every span without field tiles, save which clues could belong to them, and then X out every span that couldn't have any clues belonging to them. Now truncate the min and max positions of the field tiles. If it starts or ends inside or touching a field tile that can't have its clue, then push itself after the opposing end. If it's before the end of a field tile which can only belong to clues that are smaller than itself, then it must start after the field tile's end. And the same is true for the inverted case when it's after the start of the bigger one. And if it's the smallest possible clue of a field tile, then the max position can be more than the start of that field tile plus the size of the clue. And the same is true for the inverted case. And then truncate the min and max positions even more if they would touch another min and max positions tiles that would definitely need to be colored in. And fill in tiles using the min and max clue positions and X out the tiles that don't belong to them. Then remove the possible clues from field tiles if they are not inside their min and max positions, and if their neighboring clues couldn't fit anywhere. Now generate the span of tiles again. This time also make the possible clues for the spans that already have field tiles in them. Then remove possible clues from the spans that don't have field tiles if their neighboring clues couldn't fit anywhere. For this one I'll actually show an example, because I've only found one line where this does anything. This tile couldn't belong to a 1 because then the 2 wouldn't have enough space in between them, so it has to be x'd out. Then again, x out every span that couldn't have any clues belonging to them. And again fill in tiles using the spaces and minimum sizes that field tiles can have. And finally, using the spaces, the possible clues of the field tiles, the field spans and the current line, x out the tiles that have to be empty. This one alone is almost 200 lines of code, so I'll spare you with the details of it. Also, writing this video was already a nightmare. Also, there's a part where for every tile that's surrounded by axes, it tries to solve them by trying out both of the options, whether it's filled in or x'd out. But it can only afford to do this if the line has fewer than 100 tiles, because otherwise it would take too long. And after all of this, if the solver changed anything about the line at all, then it has to do all of these again using the changed line. This solver will never color anything incorrectly, but there are about 1 in 15,000 lines that it can't fully complete, because they basically require brute force. But thankfully that's a low enough chance that it doesn't play a role in the actual game. That chance does increase the bigger the boards are, but it's also less likely for bigger boards to fully rely on a single line for them to be able to be solved. So I think that cancels it out. So after all of this, is the new solver even faster than the previous one? Well, if we go back to the graph, I can put in the speed of the new one. At the smaller sizes, the old solver is a bit faster, since the new solver does a lot of unnecessary work for these smaller lines. But then it overtakes the old one after the lines are at least 8 tiles long, and then it keeps that pace for a really long time. And you can see how much the brute force impacts the solver when you look at how much faster it gets after 100. And obviously it's way faster than the previous one. On average, it solves a line of 1500 tiles as fast as the old solver solved a line of just 28 tiles. You might know big O notation. I don't. Anyways, I told someone in the comments of the last video that I'm making this new solver thingy, and that using it I could find the hardest 6x6 board. But then I realized that the solver won't be 2000 times faster than the previous one, and it's actually slower at that size. So instead I found the hardest 6x5 board. There are actually 6 of them that each take 20 steps to solve. And I started to really like these symbols, but I already have a profile picture, so I made them my YouTube banner. And as I said at the start, I renamed the game to Nonograms to avoid copyright problems. But without that, I could have called this video Big Cross. But now I guess it's just Nano Kilo, Nano Catagram. So anyways, I'm really happy with this solver. It did take a bit too long to make, so I tried to make the most of it. I made it possible to color in the color tiles depending on how many steps it took to solve them. And using that I can make my next video, which will be the purest form of art you've ever seen, so get ready for that one. And also I've updated the game in other ways as well. Here are the patch notes for this version if you'd like to read them. And after my next video, I'd like to move on to my next project now. This is the first game I made that I'm actually proud of, since it feels really complete and I really love playing it. I hope you enjoyed this simple and undercomplicated video, and I also hope that I'll make simpler stuff from now on. If you'd like to play the game, you can do so by clicking the Sover github.io/nonograms.html link in the description. And I hope to see you next time with an apple.